Okay, YouTube, this is my first video in my module on the properties of exponents. And so we're going to start with a couple of very simple properties in this video, the product and quotient properties, but expand those in the next video. So we're going to start with this. Recalling that the expression a to the n, where n is a positive integer, so like a whole number, positive, negative, 0, represents the product that we obtain when a is used as a factor n times. So I just want to kind of illustrate this a little bit here, but we say given a to the n, what we really mean is taking a times itself, okay? And we'll write this, we'll put a little ellipsis here, so dot, 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 all the way out to a here, where we've used a as a factor in a product, but we've done so n times. So we say n factors down here. This is the definition of raising positive base a to a power of n, okay? And so knowing that, moving forward here, let's kind of explore some properties starting with products. We say how many factors of 2 are there then in the product 2 to the third times 2 to the fourth. And so the goal is going to be able to do this, take 2 to the third times 2 to the fourth without actually having to write it out. But in this instance, we are going to write it out. So when we say 2 to the third times 2 to the fourth, let's write out what we really mean, which in this case means 3 factors of 2, so 2 times 2 times 2. That would be our 2 to the third there. Excuse me. And we're taking that times 4 factors of 2, 2 to the fourth. What becomes evident then is this. It's not 2 to the 12th that you get, but it's this instead. We say we have 7 factors of 2. And so what we're really doing, if you want to foreshadow a little bit here, is saying, well, how many total 2's we have? So in this instance, we get 2 to the third times 2 to the seventh is, or 2 to the third times 2 to the fourth is 2 to the seventh. Okay. Knowing this, however, we can take a look at any of these products down here. Now that was 2 to the third times 2 to the fourth. What if we took 2 squared times 2 to the fifth? It is not the case that we need to write all these out. However, you start to see a pattern develop after you've done a few of these. We're taking 2 factors of 2 times 5 factors of 2, and the question is how many total factors of 2 we have. We also have 2 to the seventh here. But what I want to notice is this: on the last example, 2 to the third times 2 to the fourth, they have the same, what we call bases, okay? So a is referred to as the base of this power here, recall that. But they have the same bases. We're saying how many total factors we have. Well, 3 plus 4 is 7. In this case, we had 2 factors here and 5 factors here, we get 7. So if we were to take 2 to the first times 2 to the sixth, it's like saying take 1 2 times 6 more 2's. You start to see that really what we're doing is just adding the exponents. If we said, well, what's 2 to the third times 2 to the sixth? Since they have the same bases, we're saying really how many total factors do we have? We have 2 to the 6 plus 3, or 3 plus 6 is 9. In this last instance, 2 to the fourth times 2 to the fourth, we end up with 2 to the 4 plus 4 is 8. And so in general, what we want to do is kind of express this as, say, something like this. We say 2 to the m times 2 to the n. We would get still 2 factors of 2. So the base doesn't change. What we're really operating with here is our exponent. And we're saying when you multiply two things with the same basis, what we can do is just add our exponents. So we say add exponents. And this is the key. To make it even more general than this, we can say in our property then, we say x to the m times x to the n is how many total factors of x. We say x to the m plus n. It's not the case that the base has to be 2. The base could be anything, okay? So moving forward, we're just going to talk about the quotient property here. Quotient, remember, quotient means divide. So on number 4, you notice I say write each quotient as a single power of 2 by first writing the numerator and denominator in expanded form. So for example, 2 cubed would be 2 times 2 times 2, but then canceling out common factors. So in this first instance here, we see that we have 2 cubed, so that's 2 times 2 times 2 over 2. But what I want us to recognize are a few things. First of all, the top and the bottom both share 2's, okay? And so say this 2 here and this 2 here can cancel out and they both become 1's. And what I'm left with is 2 squared. A way to write this out a little bit more extensively would be something like this. We had started with 2 times 2 times 2 on top and then 2 on bottom. This would be the same thing as 2 over 2 times 2 times 2 times 2 over 1. Remember, you multiply fractions straight across, but basically every time we have, say, a 2 over a 2, we can cancel that out because anything divided by itself is simply 1. And anything times 1 is itself, so we get left with just this quantity on the right here. So essentially, in a nutshell, we said, well, one of the 2's on top cancels out with one of the 2's on bottom and leaves 2 of these, and these are still 2 2's on top. We can put this over 1. So looking forward on letter B here, again, I just want to write a few of these out. You see the pattern a lot better. We say we have 5 factors of 2 on the top, that's 2 to the fifth, over 2 factors of 2 on the bottom. So we say these 2's would cancel with each other, these 2's would cancel with each other, and we'd be left with 2 cubed. Okay, so before we go on to the next two down here, let's kind of see if we can pick up on a pattern here. We took 2 cubed divided by 2 to the first and still ended up with 2 as our base, but 2 to the second. So we say, well, what could I do with 3 to 1 to end up with this 2 right here? Or if we had 2 to the fifth, 5 factors of 2 over 2 factors of 2, 2 to the fifth over 2 squared, and we ended up with 2 to the third. Where's this 3 coming from with respect to our 5 here and our 2 here? So if I were to write this one out, anticipating, we say we have 7 factors of 2 in the numerator. So 7 factors of 2. We'll write all 7 of those out. It's over 2 cubed. Basically, what you can start to see is this. We have 3 of these sets of 2's canceling out. But if that's the case, we really could say, well, take how many you had on top, which was 7, and then cancel out the ones you have on bottom. It's kind of like saying we get this, 2 to the 7 minus 3, okay, which in this instance comes out to be 2 to the fourth. So essentially, we had said over here with multiplying things with the same basis, when you multiply two things with the same basis, you add their exponents. What we're going to see with this property is that when you divide two things with the same basis, we're going to subtract the exponents. So again, hey, down here on this bottom one, we don't necessarily have to write it out, but we say we have 6 factors of 2 over 2 factors of 2. The 2 on the bottom cancel out with 2 on the top and leave 4 behind. But we could have gotten this simply by saying this is the same thing as 2 to the 6 minus 2, where we're subtracting the bottom exponent from the top exponent. So in general, we could say, completing this equation down here, 2 to the m over 2 to the n equals 2 to the what? We could say 2 to the m divided by 2 to the n. We'll leave behind 2 as the same base as the two things we divided with the same bases, but to the exponent m minus n. And it is very important to list this here. We say top minus the bottom exponent. Okay, always have to go in that order. So in the next video, we're going to delve into some more exotic properties of these, but this is just an example of what we mean by properties of exponents and some quick ways to do them. Cheers.